Hi there, good morning. My name is Abhay Bhatia. I'm from Zinga India. I'm here to talk about how to repair damaged or corroded hot-dip galvanized structures. Uh, I'm trying to find a solution here, as well as we want to give you an irresistible offer. Now, to talk about, we always feel that hot-dip galvanizing is the final solution to all problems, and that once that structure is hot-dip galvanized, everything will be working fine for years. But then, how often do we come across items like these? Look at these pictures, for example. Let's talk about this bottom left picture per se. You can see that the type of degradation which has happened, that you can see a lot of rust has formed near the joints. The bolts seem rusted, and the location seems to be obviously outdoors in the harsh environment, and the rust appears to be spreading along the joint interface, potentially indicating crevice corrosion. So crevice corrosion is where moisture and corrosive agents have been trapped between the joint parts. What are the contributing factors here? One is that the fasteners or the bolts are made of a different material. That can be a possibility. Second is there's atmospheric exposure, where the environment is causing moisture, oxygen and airborne contaminants like salt, sand, pollutants that accelerate the corrosion process. There is also water trapping taking place, where the design or orientation of the joint may be allowing water to get trapped and remain in the joint area, creating a consistently wet environment, which is what forms rapid corrosion. So this is something which you'll need to obviously, I'm sure all of us have seen this at our sites. Let's look at a little different image, which is the bottom right image. Here the thing is there appear to be some wind turbines in far, and the degradation is again due to mechanical abrasion, which is happening due to sand or wind blown particles, and weathering it, which is causing the premature failure of the galvanized layer. And this is also known as erosion corrosion or simply mechanical wear. Now, implication is there is a loss of the protective zinc layer of the galvanizing which is happening, and it is now susceptible to highly accelerated atmospheric corrosion, which is the case. And this is what starts the corrosion, and it spreads for a long time. Let's look at these images. I'm sure we are seeing. So you can see this is the underside of the PV cell where the structure is installed, and you can see these connectors which are used. And again, there is severe oxidation, reduction, corrosion happening. There is a heavy rust layer, a thick layer of reddish brown iron oxide is present, indicating that there is a complete failure of the protective coating. It may have been painted, the connectors, or it may have been galvanized, we don't know. And there is a severe attack on the underlying steel base metal. There is also crevice corrosion here again, and it's concentrated around the bolts, around the contact surface. There is also galvanic corrosion, that if the upper plate is steel and it's directly connected to a less noble, either it's an aluminum frame or other components, there is a presence of an electrolyte, which is like the moisture. This steel corrosion could be accelerated. There is also surface anomalies, where there is yellow and orange decoloration is there. Prominent patchy yellow-orange area, so you can see through this mouse that these colors are there. And there's a red-pink residue also, which is fouling there all the time. These are power pylon structures, a substation, this is a transformer station, where again you can see that column is being coated with a blue paint, and coating is visibly failing, the barrier protection is failing, there is rust staining which is happening, moisture has definitely penetrated the coating, and it's allowing the underlying steel to oxidize, and the corrosion products are bleeding through and staining the surface. Why is this happening? Coating failure is definitely there. The base gussets, these gussets, and the lower section of the column are experiencing heavy corrosion, probably because of water logging. there is severe rust. So there are patches of thick reddish brown iron oxide at the angles itself, and the foundation is on a concrete foundation and it's showing some cracks. So there is also soil corrosion which is taking place. So there is definitely structural vulnerability which is taking place at this. Now, I am not here to scare you, I am here to warn you that we are here to discuss a systematic structural failure that is compromising the longevity and safety of your solar assets across multiple sites. Let's be honest, things are not as good as they seem. The core problem, as evidenced by those photographs, is the premature failure of the original galvanized coating. And this is accelerating the total cost of ownership. Please understand, this is definitely going to increase your maintenance cost, meaning that your assets are moving from a passive revenue generator to an active high maintenance liability. Years ahead of schedule. See, you all are supposed to give a 25-year life. Within 10 years, you all are seeing this. I'm sure you all agree to this. This isn't just about looking bad. It is also about structural cross-sectional loss concentrated at the most crucial joints. Now, if we spoke about corrosion, we spoke about crevice corrosion. The impact of all this is, first of all, crevice corrosion is, the risk is that it leads directly to structural destabilization and the risk of complete failure under load. There is chances we have seen where the entire PV structure has collapsed due to wind, because ultimately these structures are there to withstand the weight of the PV cells as well as the wind forces. You are facing the potential need for expensive, unbudgeted foundation and column replacement. Now, I have been to the 30 gigawatt site near Bhuj. I have seen that for hundreds and hundreds of kilometers, there is no asset available except for the structure. There is no land, building, machinery. These are supposed to be graveyards where you have just kept your PV panels, your windmills, and it's supposed to keep generating revenue for your investment. But imagine after some years you see that so many of these structures have collapsed. They've fallen. What happens as a result? Second thing I want to talk about is the erosion and the abrasion. That if you go to a desert, you'll see the sand continuously blowing, causing the surface to start getting more and more rough, the galvanized layer coming out. The impact is that there is premature aging, and it triggers early warranty issues and forces you into unscheduled capex for recoating or component replacement long before the expected service life is over. Third, of course, is the chemical failure, where we saw in the transmission towers. This demands immediate, costly and complex site-specific remediation. It transforms what should be a robust structure into a patchwork of weak points. Now, what is the hidden cost? The hidden cost is very, very, very high. The cost of material is just the smallest part. Many times people say, okay, what is the cost of repairing? What is the cost of coating, etc. That is the least of your worries. What is the real hidden cost is your unbudgeted operation and maintenance. The visibility of this systematic corrosion forces you to launch expensive, unscheduled corrosion monitoring and remediation programs. I have seen it in Rajasthan, I have seen it in Karnataka, I have seen it in Andhra Pradesh. This budget line item was supposed to be empty for years to come. Imagine your CFO asks you, okay, what is your business plan as to what will be the revenues coming? You would have put negligible amount in cost of repair and maintenance. But now what's happening is the cost is becoming so sizable that whatever gross profit margin that you all have thought is completely going away. Second is the downtime. The maintenance requires a systematic shutdown. To fix the structural failures, you must power down rows of entire arrays. Every hour of maintenance on a tracker system translates directly into lost kilowatt hours loss generation and lost revenue. Then of course is the safety liability. Finally, the compromised structural integrity elevates the risk for your on-site teams and introduces a major regulatory safety liability. The current solutions are failing. It is not a question of if it needs repair, but how much time you have left before the repair becomes a emergency replacement. Now, coming back to why galvanizing is failing, that's another very important part. Galvanizing is failing for four possible reasons. One is of course the natural consumption. See, when you galvanize a structure, you are adding a layer of zinc to it of a certain thickness. Each region in the country has a corrosion chart. Now, this is sacrificial anodes. So, cathodic protection, the structure is your cathode, the zinc is the anode, and just as the car battery, you have seen the electrolytic reaction. The idea of the zinc anodes is to sacrifice itself so that the underlying structure is corrosion free. Now, every year as you check, the thickness of your zinc coating ideally will come down, because there is going to be chemical reactions which are going to take place causing the thinning of your zinc layer, which is a natural phenomenon, which is why you're putting it in the first place. So the zinc coating is designed to be the sacrificial anode. Over decades, the zinc is slowly consumed to protect the steel, and generally red rust will appear when the final zinc layer is depleted. That should be your warning sign. Second, of course, is the physical damage. Now, all your mechanical actions like scratches, abrasion, impact, bolting, etc. breach the zinc and alloy layers, and they directly expose the bare steel substrate. And the result is there is an accelerated localized corrosion which begins at the damaged point where the steel is exposed. Third is the aggressive environments. Like I highlighted, when you are going to a desert, when you are going to a very tropical area, there are very high corrosive agents. There are chloride, salt concentration in coastal areas, and there is a lot of sand which is there causing abrasion on the zinc layer at the desert. And they are destroying the protective zinc carbonate patina. So the patina layer keeps getting destroyed, and the zinc is stripped much faster than its design rate, leading to premature failure. There can also be manufacturing defects. Like I highlighted, pockets of water accumulation taking place because two cross sections have been designed wherein, let's say that a channel was installed in this way, in a C way, so all the water will keep collecting instead of being in a vertical way. So these are manufacturing defects. There are errors during the galvanization process. There's insufficient surface cleaning, and trust me, do not be relieved if you just see a galvanized structure, because now the quality of galvanizing is getting from bad to worse. There are trap chemicals in the welds. There is brittle overlay thick coating. There are lots of weak points. I also want to highlight that when you weld, you are basically burning the galvanizing layer as well, and then you are leaving the structure exposed to the environment. Now, just a bit of corrosion 101. We usually go by a standard known as ISO 12944, and there are categories of corrosion. See, my aim for this video is to educate you technically about what is happening so that you can have and you can take a much more informed decision. So, how are the corrosion regions classified? There are 5 categories, where C1 is very low, C2 is low, C3 is medium, C4 is high, and C5 is very high. Now, in this case, what is important to know is that there is an expected steel mass loss and there is a loss in thickness of the steel. Both are very important points to know. Let's talk about C1. An example is a heated building, an inside building. The environmental corrosion rate is very low, offices, schools, hotels, etc., where the grams per meter square is less than 1.3, and even there is loss in material which is up to 0.2 microns per year. C2 is low, not very low but low, where it's a rural atmosphere, clean remote areas with low pollution, inside buildings, unheated warehouses, etc., where the steel mass loss is 1.3 to 26, and you lose up to 3.5 microns, either of the galvanized coating or of the parent metal. One of them will go. Now starts the problem where C3, C4, C5 are there, where sulfur dioxide pollution takes place in urban and industrial environments, in breweries, dairies, distilleries, where up to 5 microns a year thickness is going. C4 becomes even high, where aggressive industrial areas, chemical factories, coastal areas. So I have seen most of the solar sites are between C3 and C4 and C4 and C5. And 8.5 microns a year is getting lost. And finally, very high corrosive environment where it goes up to even 10 microns a year. Now, this is very alarming, but this should not be surprising. You are seeing that extreme environments rate of corrosion is much, much faster. Now, we also talk about something known as durability. Durability means how much durable you want to make your coating system. If you want it to last for many years, greater than 15 years, you need to make it very durable. If you just want to last it for 2 to 5 years, you have low durability. So whenever any vendor recommends a coating system to you, he will always recommend that this coating system is for the class as well as the durability. So when he says C5H, it is for very high corrosivity and it is expected to last for over 15 years. Now, in terms of solar power industry, let us talk about where all which type of corrosion levels or corrosion categories are there. C1 is indoor supporting structures for inverters or control gear inside clean climate control buildings. The usual suggestion given is just a standard hot-dip galvanized structure, but it is used for uniformity and there is no issue at all. C2 also, the scene is very good. It is low, so your ground mounted solar farms in dry, remote and low polluted agricultural areas, they are good. And then 70 to 80 microns of hot dip galvanizing as per ISO 1461 is usually sufficient. The problems again, like I said, start in C3, C4, C5. C3 is a medium environment where rooftop systems are there in city centers or residential areas or near light industry, but in the low humidity zone. There we always should be putting a 80 to 100 micron galvanized layer plus a paint layer for very high durability. So I am giving the base and I am sealing off the galvanized layer with a paint system. Now C4, which is very high, where it happens, where it's solar farms like Kadwa, Karnataka, Rajasthan, where solar farms or rooftops are located 1 to 5 kilometers from coastline with moderate salt spray or areas near heavy chemical processing. This necessarily, ideally should have a duplex system. See, now why people don't you put a paint on a galvanized surface is because the assumption is always that one, galvanizing will last more than the operational lifetime of the project. Second is that I do not, if I have to provide corrosion protection after operational life, I will just recoat it with another galvanized layer. But the issue is that the so-called zinc-rich coatings are really not zinc-rich coatings in the market. They contain 60 to 65% zinc for a zinc-rich paint. Now, we are the only coating in the world having 96% zinc in dry film thickness. Now, when we say that with a lot of responsibility and a lot of tests. The American Galvanizers Association defines galvanizing as a process wherein I am imparting 95% zinc or more in dry film thickness. So we are known as film galvanizing. So while galvanized structures are left as it is not a good idea. If at all you want to use a substandard or a better than galvanizing thing, you coat it with a duplex system, that is a coating over the galvanized layer. Finally, where industrial and marine environment are there, where your solar installations are on the beach or next to harsh chemical plants. For example, in Nellore, there was a power plant for Andhra Pradesh Electricity Generation Company and Distribution Company, where we had applied Zinga on the already galvanized structures before they were assembled. So in these installations where near the beach or they are very chemical industrial environment, we usually recommend a duplex system going up to 280 microns, because like you see in that 25 to 30 microns a year sacrificing of your system is happening. So coming back to this, in C fire, when we say 200 microns is 0.2 mm, see 1000 microns makes 1 mm. So now you can imagine that if your steel is going to corrode at 0.2 mm per year, that means you're losing 1 mm thickness every 5 years. And if it's a, let's say 6 mm plate, then definitely it's going to eat, and corrosion accelerates as the thickness keeps going down. So in the extremely severe category where you're losing 0.2 mm per year, it is usually a saline, coastal and port areas and very industrial environments. You lose 0.02 to 2 in a marine and polluted urban industrial location, and it goes down. But idea is that our solar structures are always installed at places where normal human life is not really happening. Now coming back to the problem. Okay, let's talk about the problem again. As an operator, you have to provide 25-year operational warranty. Usually what we are seeing is that there was a very big boom in India where 10 years back the installation started. Now these 10 years have passed, and now we can see that the hot-dip galvanized layer is wearing off. You have done everything right. You have galvanized it as per specs. You have installed it properly. Sites are remote and resources are constrained. I feel I absolutely hats off and my salute to all the site operators who are in charge of operation, maintenance, installation and commissioning, that the resources are so constrained. You all are living in such harsh environment. The last thing you want to do is redo a job which you have so painstakingly taken. The dust is a lot, the temperatures are very high, the sites are massive. The appearance is everything. Corrosion looks horrible. You cannot dismantle and do galvanizing again. What is the usual recourse? You will just apply some paint, but you will see after 3 to 4 months or 6 months later, again these epoxy paints are coming out. Repair cycles are very expensive, time consuming, and they require a lot of coordination. So why applying paint on a rusted portion is not a good idea? I'll just explain to you this in a little technical way. So let's see what's happening here. This is basically electrochemistry in action. When the paint coating cracks, so when these cracks start happening due to expansion of metal, contraction of metal, high temperature, low temperature, the iron underneath comes in contact with air and moisture. Okay, this is all it takes to start a electrochemical reaction. Think of it like a small battery forming on the metal surface. So there's a battery forming on the metal surface. One side becomes the anode, the other side becomes the cathode. Now at the anode, the iron atoms are losing electrons. Iron atoms are losing electrons. So Fe is iron, Fe is basically electrons are getting lost. And these free electrons travel to the cathodic area. So basically in this cathodic area, they are going where oxygen and water combine. So oxygen plus water plus electrons are forming 4OH, and it is forming iron oxide, which is nothing but rust. So the Fe2 ions and the OH ions meet and they form iron hydroxide, which eventually oxidizes further into rust. So in simple terms, electrons leave the metal, oxygen picks them up, and there's rust forming in between. Now this is called non-galvanic because there is only one metal involved, which is the iron itself. There is no zinc, there is no sacrificial layer to stop the reaction. Once the paint cracks, the corrosion process keeps feeding itself under the coating. So even if you apply a paint over it, the moment there is some exposure to the environment, this problem is going to happen again. So how do you stop this? How do you protect the structures? We basically re-liquidize the galvanizing layer with Zinga. So here's how it goes. So take a look at this image. What are you seeing? You are seeing that this roller, there's a roller which is applying a liquid zinc film, which is Zinga, onto the steel. This liquid film contains 96% ultra pure zinc by weight in the dry film, almost as the same purity as the galvanized layer, which is already been done. Once applied, the zinc particles form a homogeneous metallic layer that bonds directly with the steel surface. Now, electrical conductivity which is happening is that unlike ordinary paint, the zinc layer is electrically conductive. The zinc particles are in contact with each other and with the steel substrate, creating a continuous metallic network. That is very important to note. This means that the electrons can flow and enable a cathodic or a galvanic protection, just like hot dipping. How does it help? The barrier is protected because the film seals the steel from air and moisture and it acts like a coating. There is also galvanic protection, wherein if the coating is getting damaged, the zinc will sacrifice itself, protecting the exposed steel by releasing electrons. There is also a self-healing action. The zinc corrodes to form zinc oxide and zinc salts that fill micro cracks, sealing the film again. The use cases are that Zinga can be applied on the bare steel or even on over existing hot dip layers for repairs and reinforcements, something which you cannot do with molten galvanizing. It combines the advantage of hot dip galvanizing, which is nothing but active cathodic protection, and paint coating, which is the ease of application and recoating. So this is a very important way how Zinga is working on this. Now coming back to our chemistry 101, now we are showing to you how galvanizing helps protect the structure. Wherein when you have a galvanizing layer, you have no corrosion. Okay, so let's understand how it's working. Zinc is more reactive than iron. So it willingly will keep giving up its electrons first. So what will happen is zinc will become Zn2 plus 2 electrons, and then it will form, these 2 electrons will go and they will form a homogeneous layer with the oxygen and form zinc oxide. So this zinc oxide will be your protective layer. No longer iron oxide is being formed, zinc oxide is being formed. As a result, what's happening is your iron structure is going to remain untouched and protected. So it is an active cathodic system which is happening. See, mind you, we are not giving you just some patchwork. We are basically healing the entire coating system. And on a galvanized layer, there is nothing better that works. So zinc is combining with oxygen, forming zinc oxide, which is a stable compact layer that seals and protects the surface even further, because zinc is more reactive than iron. Our conclusion is that the key to achieving a very high, which is 25-year durability on the hot dip galvanized structures, is using the hot dip galvanized plus Zinga duplex system, guaranteeing immediate repair of the physical damage and extended corrosive resistance in the C4 C5 environment. So I hope this was a good brief of how Zinga acts and how cathodic protection takes place in a film galvanizing system. Now I want to talk about, before I go to the irresistible offer, our overall experience with Zinga so far. So we have seen that all these structures are going to keep getting corroded with time, and if the operators are not going to work towards solving it once and for all, this is going to get from bad to worse. So what we started doing initially was we appointed a national network of corrosion applicators, so anti-corrosion applicators, that is the coating systems, and we were able to basically develop this network so that they could go to the most remotest of sites and repair the systems. So over there, I'll just like to show you some videos which we have downloaded. So our people go to your site and they literally carry out corrosion protection like this. You are basically cleaning the surface and then you are applying Zinga through a brush, spray or roller like this. And what we are doing is also, you can see the sharp edges, the corner edges are being coated first. That is known as a stripe coat. Now this stripe coat makes sure that there is no corner corrosion, because usually the zinc layer is little less in these cases. So that is what is getting protected. Along with that, what we do is, once we go to a site, we will check the conditions, and then through Zinga Belgium we develop a coating system. And this coating system talks about your surface preparation, your application, your precautions. So Devi Coat was one site in Rajasthan, and what we realized, it's galvanized steel, it's a desert environment, exposure category is C4, very high, and we said that surface preparation is needed. Zinga unique system is required, and you can see the required DFT and the spreading rate, application method, and overcoat, touch dry, everything is mentioned. So we talk about how the this is a case study where how we are solving a customer's problem. We make general notes. So these notes are given to the customer before they sign up with us for the actual contract, so that they are aware as to what we are going to do. Because so many remote sites, so many applicators, the uniformity in application may not be correct. So that is why we create a lot of documentation in this process. So we say refer to the technical data sheet. We say that make the surface proper, do a bristle test, and when you tie up with us, our people will go and do all this for you. All you have to do is show us the site, do a trial application, and if you're satisfied, we will do the entire repair of your asset, and we will give you the lifetime warranty, which is 15 years of what is needed, or it depends. So that's why we need to come to the site and check it first to see how bad the corrosion is, and then we create a system, and then we do the application. We do pre-cleaning, we do welds and repairs, de-dusting. So you can see the kind of documentation which is going in this. There is a stripe coat which is applied, then there is a full coat which is applied. We have measuring instruments, wet film thickness meter, dry film thickness meter. We also have acceptance criteria, and this is the entire system which is made and coated. So now let me come back to my irresistible offer. Now this offer is as a thank you gesture to all the solar panel operators, maintenance teams, installation teams, etc., that we want to help you have a permanent solution, so that once you install your site, your asset at the site, you don't need to look at it again. Now before I proceed, I also want to tell you the ideal time to apply Zinga on your structure is not after installation but before installation. Simply because when you do it before installation, it is much easier. All your sections are exposed. You can easily turn them around. You can easily apply the coating. You are not constrained by any objects, any PV panels, and of course you don't need to have downtime. When I went to Bhuj, where hundreds of kilometers of solar panels were there, lot of assets were still to be installed. See, out of 30 gigawatts, 6 or 7 is done. It's only been 1/5. So I'm here addressing NTPC, Adani, SAES, all these asset installers, that please understand that you all have, the battle is just starting, and you don't want to have a situation where again after 5 years you have to float a RFQ for repairs, maintenance, and then increase your OPEX by almost 10 to 12%. I am here to save your cost now. Call us immediately and let us apply Zinga before your structures are getting installed. Now, here's the offer what we are going to give you. So, drum roll, and here it is. We are giving you a 15-year C5 environmental turnkey pledge, wherein we are saying we will eliminate 0.2 mm per year steel loss, and we will secure your asset immediately. what we are recommending is as follows. We are saying in phase 1, we will charge you 4.5 lakhs plus GST for coming to your site, doing a trial application, preparing a report and submitting it to you that these are your assets, this is the current state, this is the expected lifetime without Zinga, this is the expected time with Zinga. We will come down there to your site and pitch this to you. In phase 2, if you agree, wherein you are committing to us minimum 2000 square meters of area, wherein we expect the contract value to be somewhere to the tune of 21 lakhs, we will refund or adjust the 4.5 lakhs which you have paid us for the trial application. So the net contribution is only 16 lakhs 50,000 for 2000 square meter area, wherein we are taking care of the coating, the material cost, we are taking care of the application cost, and we are making sure that your net cost for protecting your structure for 15 years is 1050 rupees a square meter. It becomes the effective cost in totality, out of which 4.5 lakhs anyways will be adjusted. So if our certified applicator or our application fails to maintain the cathodic protection, we will provide a replacement material and reapplication of service at no cost. So this is taking into consideration a minimum area of 2000 square meter you have to give us, and we will provide cathodic protection. We will ensure the application is done by professionally trained Zinga approved applicators. We will have an inspector who is a level 2 NACE certified inspector, certifying and giving the warranty card to you that this is how we have applied it. So we are very, very confident about our product and our application capability, and we recommend that you explore this. Zinga is present in over 120 countries, so it's not a local fly-by-night operator. It's a product which is there since 1966. All of Belgium, all assets are coated with Zinga. In India, the notable applications in non-solar are Mumbai Airport 1B, DY Patil Stadium, Wankhede Stadium. All of them are being coated with Zinga. So these are iconic structures which we are coating. They are available in all these countries. The advantage is 96% zinc with dry film thickness. It has a passive barrier. It's a one component zinc coating. It is not a paint. The working principle I have already explained to you. It has, you can apply it by brush, spray, roller, that we will apply it for you. You can apply it even in a damp environment, when it's drizzling, where the last thing you can do is apply paint, you can apply Zinga. The temperature range is extreme, -22 +45, which is why we recommend winters are the perfect time to apply. There is no energy loss, there is no deformation, there is no heat involved. It's a heatless process. You can use it as a new system altogether where you have not galvanized it, or you can repair the galvanized layer. It has a very quick drying time. It touch dries in 10 minutes. The second layer can be applied within 1 hour, whereas paints take 6 to 24 hours, so a day is wasted. It will never peel off or never, it's not brittle. It will never be, it will be compressed or squashed, it will not crack, nothing will happen. Local damage is very easy to repair. Welding, very easy to repair. So over welding, we see a lot of touch-up sprays being used and coatings being used. You can see the sheer amount of stress the paint is going through, wherein on the rollers of these windmill turbines, you can see that the zinc oxide layer is coming out. So if I show my mouse here, zinc oxide layer has come out, but the active cathodic layer is still there. Galvanized structures can be recharged, so you can basically see here we are showing you a zinc layer, how it's forming a homogeneous layer. They are no longer distinct. With time, it becomes a single homogeneous layer. It has a special resin, a patented resin. It forms a galvanic couple, and it has a very high amount of metallic zinc. The granules itself are very big and the contact surfaces are high. Now, we've got a lot of tests. Testing, there's absolutely no problem. Zinga has anything which is reaching -850 millivolts is considered as cathodic protection, and Zinga passes that. Immersion test through salt spray, we are having certificates of 10,000 hours of salt spray. No other coating in the world has that kind of thing. It can be top coated with a large number of top coats, but we usually recommend for solar leave it as it is so that you contact us after 10 or 15 years again to apply the system again. It contains non-toxic elements, so it's portable. And it has unlimited shelf life. So if you order a lot of Zinga, don't be worried that it will get spoiled. We are having batches which are 20 to 25 years old, unopened and absolutely fine. Now, when you compare it to Hot-Dip, the amount of time needed for Zinga is less than a day as compared to what takes 4 days in a Hot-Dip process. So 2 coats of Zinga give the performing equivalent of 320 to 360 microns traditional coating system. A lot of advantages, lot of test reports are there. We are having a lot of European certifications, Indian certifications, etc. It is passing C5 IM also, 120 micron Zinga. So there is absolutely no problem. So I strongly recommend, we have a lot of microbial induced corrosion resistance as well, and friction coefficient is 0.52. So the abrasion is retained in the whole process. References we are having everywhere. So Indian references, Power Grid is our standard customer, AP Genco is our customer, NTPC through its various alliances are our customers, Power Pylon manufacturers are our customers, everyone's a Zinga customer. So these are some of the international testimonials wherein galvanized bridges sections have been coated and repaired. Something which was applied in 1985, even in 2013 was absolutely fine. This is in Europe. You can see some of the bridges, and even in Turkey there is a Osman Ghazi bridge. It's the 4th largest bridge. This is coated. So you can see the amount of Zinga also coated on this, and you can hydraulic launchers everywhere you'll see Zinga. So I hope these are Chinese bridge where we've coated with Zinga. I will definitely be there to answer any of the questions. In wind, we are saying put the primer layer as Zinga and then put a top coat and forget about it for next 20 years. That is the kind of confidence which we are displaying. Wind turbines, etc. So this is a plea to the renewable energy sector in India. Take advantage of this coating. We are available. We are based in Mumbai. We are having dealers and distributors all over, and we will take care of your assets. See in offshore the amount of corrosion, how we have protected the structure and applied a top coat. So this is the kind of way we do. We are very technical sound. Submerged structures also we take care of, and then we apply this coating. Marine, silos, everywhere. Storage tanks, absolutely everywhere we are doing Zinga application. Crash barriers also, which are galvanized as a repair system, we use it. Signposts also we use it. Towers we use it. So these are mast lamps which we are using it. Pylons, of course, I spoke about. Power plants I spoke about. And you can ask us for whatever testimonials, whatever references are needed, whatever test reports are needed. We'll be happy to give you. So I hope this was a educational session for you. I strongly recommend you get in touch with us and take advantage of the trial. See, don't think of the cost in actual. Think of the per square meter per year cost. Think of the life cycle cost which is there, and I'm sure you will benefit from it. So that's it. This is the pledge which we are offering, and thank you very much. My name is Abhay Bhatia, and I hope we interact in the future. Thank you.